Hey guys, now we are going to talk about finding the sum of an infinite series. So when I use the word series, that refers to the sum of all the terms of a sequence. An infinite one is a list of numbers that's infinitely long. So can you ever find the sum of all the terms in an infinitely long sequence? So if the sequence was like this, 3, 6, 9, 12, can you find the sum of all the terms of that sequence? Well, sure, because it ends at 12, you can add 3 plus 6 plus 9 plus 12. But what if it went on forever? 3, 6, 9, 12, 15, 18, and it just keeps going forever. Now, is it possible to add all the terms of that infinitely long sequence? And the answer is no, because that sum is actually going to be infinitely large. But there are some times when you could add all of the terms of an infinitely long sequence. When it's written like this here with a plus between each, that represents the summation of the entire thing. That is a series. So here is an infinitely long sequence, or an infinitely long series, and I know it's infinitely long because dot, dot, dot. And this one is arithmetic with a common difference of 3. Because the numbers are just going to keep getting bigger and bigger and going up by 3 each time, but they'll get infinitely bigger as we go along, the sum is not a finite number. So can you find the sum? So can you add this entire series and find a finite answer? No. The sum is going to be infinitely large. Okay, here's another arithmetic sequence with a common difference of -5. Could I add all the terms of this infinite series and find a finite answer? The answer is no, and this sum is going to be infinitely small. How about this geometric sequence with a common ratio of 2.5? I'm multiplying by 2.5 every time, and you see the numbers are getting bigger and bigger, and they're going to continue to get bigger toward infinity. As I add all these up, once again, I'm going to have, so it's a no, I can't add them together because it's going to be an infinitely large number. Okay, and here's a case where it's geometric and r is 1/2. So I'm adding 1/2, 1/4, 1/8, 1/16. Now these numbers are not getting infinitely larger or infinitely more negative. So here, I guess it would be an infinitely large negative number. In this case, these numbers are getting infinitely closer to 0. In this case, I could add all of the terms of this series all the way to the infinity term. That is only possible when you have a geometric series. Never possible for arithmetic, only geometric, when the absolute value of r is less than 1, which means r is less than 1 but greater than -1. If that is the case, then you can use this formula to find the sum of an infinite series. So if it is possible, we want to find the sum of the infinite series. 1, 1/2, 1/4. This is the same one as what we had up here. And we already know r is 1/2. Well, how do we find that r? Just to be sure, we could do 1/2 divided by 1, so term 2 divided by term 1, and that's 1/2. And then term 3 divided by term 2, 1/4 over 1/2. The outer loop here gives me a numerator of 2, inner loop denominator of 4, which is 1/2. So we have a common ratio. It is geometric with an R of 1/2. So it is possible. So the sum of this infinite series is term 1, which is 1, over 1 minus the common ratio of 1/2. So it's 1 over 1/2. 1 minus 1/2 is 1/2. 1 divided by 1/2. The outer loop gives me 2. The inner loop gives me 1. The sum of this entire series is 2. Or at least infinitely close to 2. Okay, so this next one, we're going up by 1, then up by 1.5. So it looks like it's going to be geometric again. So the first division is 3 over 2, which does not simplify. The second division is 4.5 over 3, which is the same as 45 over 30. And 15 goes into 45 and 30, 3 times and 2. So it is geometric. R is 3/2, and that is not between -1 and 1. So the sum here has no limit. The sum is infinitely large. Okay, next I'm going to erase some of what I've got over here. Just clear some space. Okay, so we've got 1 over the square root of 2. So that's root 2 over 2. Then we've got root 2 over 2 over 1, which is root 2 over 2. Okay, and that is between -1 and 1. Okay, so we can find the sum. S sub n equals, I should make a note that it is geometric, and R is root 2 over 2. So the sum of the series is the first term, which is root 2, over 1 minus root 2 over 2, 1 minus R. Okay, and 1 is the same as 2 over 2. So we've got root 2 over 2 minus root 2 over 2. So our outer loop is 2 root 2. Our inner loop is 1 times 2 minus root 2. We cannot simplify because there's not a 2 outside here, there's not a root 2 here. So what I can do to get the to rationalize the denominator here is multiply top and bottom by the conjugate of the denominator, 2 plus root 2. Okay, so I've got 4 root 2 plus 2 root 2 times root 2, which is 2 times 2, which is 4. Then in the denominator, 4. And I've got minus 2 root 2 and plus 2 root 2. And I drew one of those incorrectly, so let's try that again. How about this? 2 root 2 and minus 2 root 2, and those cancel. Then I've got negative root 2 times positive root 2, which is minus 2. So I've got 4 root 2 plus 4 over 2. And all three terms are divisible by 2, so I've got 2 root 2 plus 2. And my last one. It needs to be geometric, so I'll look for a common ratio. 9 over 5, and that doesn't simplify. Then I've got 81 fifths over 9. We'll make that 9 over 1. So I've got 81 over 45. 9 goes into 81 9 times. 9 goes into 45 5 times. I've got a common ratio, so it is geometric. And R is 9 fifths, but 9 fifths is not between -1 and 1. So the sum of this series has no limit.